All right, guys. If you have not finished the vocab sheet, make sure you get those turned in as soon as possible. Thank you. For those of you, 1, 2, 3, 4, 5, 6, the 6 of you who have not finished the chapter test, there should be some over there. We'll need you to do that tomorrow during CHAMP. I'll make sure to call you down if you forget so that you guys can come down and finish the test. Also, with the vocab sheet, I did put the PDF of the glossary in Google Classroom, so you have access to it there. Now, what we're talking about in Chapter 10 is going to revolve around circles, interestingly enough. So, some of y'all have done the vocab sheet already and kind of have an idea of some of the different key terms for this chapter here. But a circle is the set of all points in a plane that are equidistant from a given point called the center. So we have a center and the set of all points equidistant from that point. And a circle with center P is called circle P. So we can call it circle P, or we can draw a circle with a dot and then the letter P. So we can name it by its center. So we can draw a circle and then the center point P, or we can call it circle P. So it's named based off its center. Now we have some different segments and parts of the circle. A segment whose endpoints are the center in any point on the circle is called a radius. So a radius is just a line from the center to a point on the circle. And if we have more than one radius, we call them radii. The plural of radius is radii. A chord is a segment whose endpoints are on the circle. So any line that connects 2 points on the circle is a chord. Now we have something called the great chord, and a great chord goes through the center. And we call it the diameter. The diameter is a chord that contains the center of a circle. A diameter is a chord that contains the center of a circle. So a line that connects 2 endpoints and goes through the center is the diameter. Questions on any of this so far? So radius and diameter are terms we've heard before. Secant is a line that intersects a circle in 2 points. So we call it a secant line, secant segment, any type of line or segment or ray that connects or intersects the circle at 2 points. If it intersects at 2 points, it is a secant. A tangent is a line in the plane of a circle that intersects the circle at exactly 1 point. Secant intersects the circle at 2 points. Tangent intersects it at 1. And the point that the tangent line intersects the circle is called the point of tangency. We can have a tangent ray, a tangent segment, but they're going to intersect the point at one spot, and it's called the point of tangency. Intersect the circle at 1 point. Any questions on any of this here? Now, if we look at this figure, tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. Now, the first one we're going to look at is AC. Radius. Because a radius, by definition, is a segment that connects the center of the circle to a point on the circle. That's it. B, AB. Connects 2 points on the circle and goes through the center is the diameter. DE. So DE is this line here. It intersects the circle at how many points? Tangent. And AE does intersect it at 2 points, so it would be. For tangent ray DE, what would the point of tangency be? B. Point of tangency is just the point it intersects the circle, the point that it is tangent to the circle. And there's going to be a lot of times, I think I've said it in here before, mathematicians are not the most creative with naming things. With an isosceles triangle, the base side of the triangle, the angles connected to it are the base angles. They kind of call it what it is. And we'll see that a lot, especially in this chapter here. In example 1, what word best describes a G? Secant. So we can call it a secant segment. So we can call it secant or secant segment because it's a line segment. It's secant is a secant line segment, secant segment. CB. Yeah, so AG is secant. CB. C is the center and it connects a point on the circle, yes? So it is a. In example 1, in this figure here, name a tangent, so a tangent line and a tangent segment. So what would a tangent line be? And we have to put a line above it to signify that it is a line. Now, how can we name a tangent segment? So DB, and we have a line segment above it, yes? Could I have said DE? But instead of drawing a line above it, I draw a segment. So really, for the first one, we could have said DB, but have a line above it. Because for the tangent line, it's any line that intersects the circle at exactly 1 point. So DE and DB both work. For a segment, DB, line segment, DE, line segment. Questions on this here? You ready? Yeah. Because we could say EB and put a line above it, or we can say EB and put a segment above it. Any other questions on this here? Our first theorem for this chapter, tangent line to a circle theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of a circle at its endpoint. So if we have this here, point P is the point of tangency, and we connect the radius to it. We have the radius that connects to that point of tangency. It and the tangent line should make a 90-degree angle. Not so much, it's not connecting to the circle because that's a curve, but the radius and that tangent line will make a right angle. So, looking at this here, ST is tangent to the circle. Well, is ST tangent to circle P? So TP is a radius, yes? And we're wanting to know, is ST tangent to it? Well, by the definition, these two need to intersect at a right angle. Well, what kind of shape do I have here? A right triangle, yes? So if ST is tangent to the circle, then this here should be a right triangle. And if it is a right triangle, then a squared plus has to equal. And which of these three segments would be the hypotenuse? Now we know that for a few reasons. One, it is the biggest side, but also because it's opposite where the right angle should be. Because if this is a right triangle, at point T, that's where the right angle should be. So SP should be the biggest side. Now we can plug 35 and 12 into the other two sides. And see, does this indeed make a right triangle? Now at this point here, we can grab a calculator, and we can say 35 squared plus 12 squared is 1,369. So the entire left side of the equation is 1,369. Now we need to take 37 squared. 37 squared is 1,369. Yes, this is true. The Pythagorean theorem is true, which means this is a right triangle. So is ST tangent to circle P? Yes. T is tangent to circle P. Questions on this here? No. T. So we want to see if this is true here. Now, one thing we can say for sure is that we need, at this point T, to be a right angle if it's tangent. Now, again, just like before, we're going to be using Pythagorean's theorem. A squared plus B squared is equal to C squared. C in this case would be 51, and it is in the right place. Because if we were given a length that's less than that, it wouldn't work out. Yeah, so it should be opposite the right angle. Now the other two sides, A and B, are going to be our other two, 44 and 24. Now 24 squared plus 44 squared does indeed equal 51 squared. Then ST is tangent. (24 squared plus 44 squared is 2,512. And if we do 51 squared, we get 2,601. So we can say not tangent, or we can say ST, not tangent to circle P. It's not tangent because Pythagorean's theorem does not hold true. Any questions on any of this here? So let's look at this one here. So we want to determine if DE is tangent to circle C. If that's true, we need to have a right angle at this spot here, yes? So it means the hypotenuse is what? So what is 2? Is 2 the entire length of CE? It's the length from the point on the circle to the outside, yes? Now the big question is, what is the length from C to the circle? It is indeed 3, because the radius is the length. It's the same all the way around. So what is CE? And again, I included this one here just for that particular reason. It is indeed. 3, 4, 5, where 5 is the hypotenuse and the other two sides are 3 and 4. We do get this here. And if we did 3 squared plus 4 squared in the calculators, it would be 25. And 5 squared is. So DE is tangent. And that's it. Any questions on any of this here? Feel pretty good about this so far, yes? Well, we can take that and put it into an application of sorts. And if we look at this here in the diagram, point B is a point of tangency. Find the radius R of C. So since point B is a point of tangency, it means AB, line segment AB, is tangent. Line AB is tangent. B is a point of tangency, so line AB has to be a tangent line, which means this here is a right angle. Yes? Okay. Which means Pythagorean's theorem still holds true. So this here, Pythagorean's theorem is still going to hold true. This is still going to work. Now, what we know for sure is that 80 feet is one of our sides. So we can call it A. What is the other side going to be? One of the other sides is the radius. Because the hypotenuse is the side opposite the 90 degrees, which is this whole side here. Yep. 50 plus r squared, r plus 50 squared. Either one of them works. So we'll see how this works. It's been a minute since you've had to multiply r plus 50 to r plus 50 squared. But this will actually work out quite nicely. Now, if we look at this here, so, well, before we start solving, are there any questions on how we set this up? A squared plus b squared? Yeah, so we're just using Pythagorean's formula and plugging in our values. So r plus 50 was the hypotenuse, because we just added those two lengths together. You're good. And then our other two sides are r and 80. Now, we can plug 80 squared in the calculator. It's just a number. 80 squared works out to be 6,400. 8 times 8 is 64. Then we have our two zeros. R squared as well. R squared. Yes. Now, r plus 50 squared is the same as r plus 50 times r plus 50. Now, on the left-hand side, I'm going to rewrite this as r squared plus 6,400, r squared plus 6,400. I just like having the r squared first. I just kind of like it in that order. There's no other real reason to it at this point. Now, the other side, we're going to use our distributive property. We're going to multiply through. R times r is r or r squared. Because whenever we multiply something by itself, we say it's being squared. Then we can do r times 50, which is going to be plus 50r. Then we can do the same thing with 50. 50 times r is going to be plus 50r. And lastly, 50 times 50 is 2,000 500. Because 5 times 5 is 25. Then we have our 2 10s. Then we can combine like terms. Exactly. Because we still have r squared. 50r plus 50r is 100r. 2,500. Now, the first thing we want to do, and we'll get into this especially, you got into a little bit in Algebra 2, not, you haven't done that yet, but Algebra 1, we want to get r squareds on the same side. So I'm going to move it from the left to the right. So if I subtract r squared from the left-hand side, r squared and r squared will, what I do to one side, we have to do to the, and r squared minus r squared is, so what we're left with is 100r plus 2,500 is equal to 6,400. Yes, and this is why I said this one works out kind of nicely, is because our r squared terms cancel out on both sides. So we're left with this here. Now we can subtract 2,500. We can subtract 2,500 from both sides, which will tell me that 100r is 0, 0, 4, 5, 9, 3. And lastly, we can divide by. So what's the radius? In the diagram, point B is point of tangency. Find the radius of circle C. So the radius is? Hopefully that was not as bad as it might seem. The middle got a little weird and a little bit challenging, especially when we started talking about r squared. And it looked like it was going to get very complicated, but then it got simplified down very quickly. Questions on this here? External tangents of a circle. If two tangent lines meet at a point outside of the circle, then they're congruent. Two tangent segments from a common external point are congruent. So what that's saying is RS is congruent to ST. That's it. So we can say what? RT is 28, yes? Now, unfortunately, it didn't ask for just RT's length, because if it did, we'd be done. So RT is tangent to circle C at S. RS is tangent to circle C at S. RT is tangent to circle C at T. Find the value of X. So we know that 3x plus 4 and 28 are the same. And really, if we did this mathematically, you don't have to write this all out. We would know that RS is congruent to RT. And because of the definition of congruent segments, we can say RS is equal to RT. But we know that RS is 38 and RT is thank you. And now we can just solve. So the first thing we can do is subtract 4. Telling us that 3x is equal to divide by 3. Do we need to plug it back in? Just to find x. I mean, even if we did, we know that RT would be what? 28, because the other side is 28. Questions on this here? We ready for the next one? Almost. So let's look at this here. So we know that these two segments are congruent, yes? So we're saying that x squared is equal to 9, yes? If we solve this in Algebra 1, what would our first step in solving be? We would square root both sides. This is called the square root method. Whenever we don't have a middle term, an x term to the first power, we get x squared by itself, get all the numbers on the other side, and take the square root of both sides. And the square root of x squared is x, yes? Square root of 9 is 3. And whenever we take the square root of both sides, we add a plus or minus. Add a plus or minus. Because what we're saying is what number times itself is 9. Well, we know for certain, and we've seen it enough times, 3 times 3 is indeed 9. What is negative 3 times negative 3? It's still 9. Negative times a negative is a positive. 3 times 3 is 9. Now, for most all geometry that we've done so far, when we encountered a problem like this here, we threw out the negative case. Because when we talk about a length cannot be negative. A distance can't be negative, right? But if we look at this problem, if I plug it back in there, that square is counteracting the negative, yes? So realistically, that value of x could be positive or negative. Because the length is x squared, it takes care of that negative case. So this is one of the few times that it actually could be negative for the value of x. Questions on this here? So this here I don't think is necessarily in the notes. I still do want to talk about it. Now we have coplanar circles and common tangents. In a plane, two circles can intersect in 2 points, 1 point, or no points. So either 2 points here, 2 points of intersection, they overlap each other. 1 point, they're essentially touching at that point of tangency, so we can say the circles are tangent to each other, or no points. And one of the types that we have where there's no points of intersection is called concentric circles. Circle inside of a circle. I think some of you all have seen this before. What's another name we give for it? Bullseye. A bullseye is concentric circles. It's circles inside of circles. Now, coplanar circles that intersect in 1 point are called tangent circles because they're tangent to each other. Circles that have no common points are concentric circles. A line segment that is tangent to two coplanar circles is called common tangent. So if it's tangent to both circles, it's called a common tangent. Now, we have two different types of common tangents. Ones that are internally tangent and ones that are externally. Internally tangent intersects the circles that joins the center. Externally do not. So if I connected a line between the two centers and that line of tangency intersects it, it's called internal. If it doesn't, it is external. And the way we can think about it is if it crosses between them, it is internally tangent. If it doesn't, it is externally. So if we look at the first one here, these two blue lines are tangent to the two circles. They intersect the circles, each circle individually at 1 point. But does it cross between them? No. So they're externally tangent. The two red ones do indeed intersect each circle at 1 point. But since it goes through the middle, it intersects that line connecting the two two centers. They are internal. And that's the only real difference. Now the first one, we have 4 common tangents. We have 2 that are external, 2 that are internal. And this is with no intersections. The circles are not intersecting each other. If we have 1 point of intersection, we have 3. We'll have 1 internal, the line that actually connects those 2, and the 2 external. So internal is in the middle between them. External is outside. Because internal intersects the line that connects the 2 centers, or goes between the circles. If it doesn't go between the circles, it's not internal, it is external. And if the circles have 2 points of intersection, there are no internal tangent lines because there's no way to cross them without intersecting more than once, making a secant line, but it does have the 2 external. That make sense? Homework is on page 480. Problems 5 through 10, 15 through 18, 19 through 21, 29, and 30.